Right, this group they'll introduce themselves, Water and Health Engineering. They participated in our International Senior Design Program, and they traveled to Panama and worked with the community there in August. And then when they came back, they completed this design project for a water supply system.
Hello and good morning. We are Water and Health Engineering. My name is Melina.
I'm Victoria.
I'm Megan.
And I'm Nathan.
And today we are going to talk about our water distribution system for Mocambo Arriba, Panama. So real quick, here's just a brief overview of where we're going to go throughout this presentation. We're going to start with a brief background of Panama, the community itself, and this project overall. Then we're going to talk about our objectives, what we wanted to accomplish when we attacked this problem. Then we're going to talk about some of the major assumptions we had to make when we wanted to start our design. Then I'm going to talk broadly about the proposed design overall, just a broad overview, and then we're going to go into more specifics with talk about the storage tanks that we designed, and then the supply system, which will be broken up into two subsections, the long-term recommended and the short-term alternative. And then we're going to finish up the specific stuff with the distribution system. And then we're going to end with our recommendations and just general discussion points.
All right, so background of if you guys don't know where Panama is a country in between Central America and South America. So what's important about this that we'd like to note is the area known as the Panama Canal was previously occupied by the United States. Thus, the United States had a very strong influence and presence in Panama. And then the Panama Canal was turned over again to Panama in 1999. So because of this influence in Panama, the area around there is more developed than neighboring countries. So that plays into our project because they're expecting a higher level of development in this project. So then the design site that we're looking at specifically is approximately 8 miles from Panama City, as you can see in the bottom right here. And from the Panama Canal, it is approximately 6 miles. All right, so for the community we were working with has a population of approximately 2,000 people. And now this is divided into 4 sectors, as can be seen on the right here. So this is important because it plays in later to how our tank design was created based on where the population is needing more or less water. And then some of the current conditions that they have down there right now is they either get water from tanker trucks, as you can see in the bottom left. These come about once a month, so they're not meeting the needs of the population, or people take water from the local streams, which has water quality concerns. And then as well, during the dry season, all the rivers dry up, so they do just not have enough water. All right, so there were 2 previous senior design teams that created designs for this. However, they were not able to go to Panama due to COVID. So this left them with some shortcomings or wrong assumptions within their designs that we were able to quickly see and remedy with our own design. So the first design was one from the eastern point, as can be seen in the left picture. This was through the mountains and was a completely gravity-fed system. The second design was from a supply point in the north and came around this road over here to the northwest. And the problem with this was it's much longer of design, but it's through much more developed roadways. All right, so then some of our objectives that we are looking to solve with our design specifically is number 1, making sure that they get enough water per day. So this was approximately 13.2 gallons per person per day. And then we also wanted to make sure that we're operating within good supply pressures. So we were striving for between 15 and 75 PSI, with the maximum operating pressure being approximately 100 PSI. And then we also wanted to select a pump that will efficiently pump water through, considering that the site that we were looking at was right in the mountains of Panama. Our system did see a design elevation change of over 400 feet. So we wanted to overcome that with our pump. So then we also wanted to develop an accurate bill of materials for the community, because the people that would be constructing this are in Panama. There are a lot of supply chain differences or even just general construction terms that don't translate over, or they have different standards. So we wanted to provide them with a materials list that would be much more easily used by them rather than cost layout, because they would be making some of their own changes. And then finally, we have some of our assumptions and estimates that we went on when designing this project. So again, is that 13.2 gallons of water per day, which is how we dictated the tank size. And then also the number of houses per sector dictated the tank size, with sectors of higher populations needing a larger storage tank. And then we also standardize a 5-person household size for the community. This did seem like a good representative. And then we have created 2 daily demand curves, one for the residential houses and one for more commercial buildings such as the health center or the school. And then finally, there were some elevation inconsistencies. When we were in Panama, some of the equipment we were using was not quite what it could be to what we use in the US. So there were some inconsistencies that we had to go back and calibrate with Google Earth.
Okay, now I'm going to talk just broadly about our proposed design. Our proposed design is a 2-part system. The first part being a supply system. This is what's going to connect to a regional municipal system, and it'll pump that water up to 2 storage tanks within the community. These 2 storage tanks are located at high points, so that from there it can go into the second part of our system, the distribution system, which gravity will take the water from the tanks to the houses and buildings within the community. The sketch on the board here kind of shows what we're trying to accomplish. And it'll be pumped to high points using a pressurized system, and then gravity will take it down to the people. Furthermore, a little bit more about the proposed design is there were multiple connection points considered, as we talked about earlier with the other teams. And then ultimately we had to look at different points of connection, which I will get into later. But regardless of where we connect to, it'll be part of a regional municipal supply system that takes the water from the Chilibre water treatment plant. So doesn't matter where we get it from, we will be getting these people clean, safe drinking water. And it's important to note that the community and the Chilibre water treatment plant are within the same watershed as the Panama Canal. So the water treatment plant gets its water from Lake Alajuela, which is the same lake that supplies fresh water to the Panama Canal. So it's important to at least acknowledge that we will be taking additional water from these areas, which will put a little bit more stress on the freshwater resources in that area.
So getting a bit into these water reservoir storage tanks, we had to select a couple of locations that would be ideal to place these tanks in such a way that it could gravity feed the village. And to that end, we selected a northern point and a southern point after consulting some topographic maps of the area. So overall, these storage tanks were designed to have a reservoir of about 45,000 gallons. And the main reasoning for that is considering the population and the daily usage, we wanted to have about 1.5 days worth of water for the village. This gives them a bit of a buffer in case anything happens to the water supply. If it's cut off, there's still a little bit more than 1.5 days worth of water. So going more specifically into the details of these tanks, the interiors of these tanks all have, they're a bit modular in their design. They have a 10.5 by 10.5 footprint on each of the interiors of these square tanks. The northern tank has 2 of these square tanks, and the southern tank has 4 of them. These are made out of standard 8 by 16 by 8 cinder blocks, concrete to compose the base and the lid, and rebar in addition. And on the interior of the tanks, they're coated with hydraulic grout.
All right, now I'm going to talk in a little bit more detail about the supply system, which, as I mentioned earlier, is going to be separated into 2 subsystems. We have the long-term recommended solution, which is where we spent most of our time, and you guys can see that in an image on the left of the screen, with a connection point in the northern city of Villa Gracia. And then I'm going to talk a little bit about the short-term alternative that, for reasons I will discuss, we had to kind of make at the last minute, which is shown on the right, where we have a connection point in the eastern city of Cerro Pinon. So first, the long-term recommended solution. This has a connection point in the northern city of Villa Gracia, as I discussed multiple times. We decided that this was the best connection point due to construction feasibility after talking with local contractors in the area. And we were also able to walk a couple of the different paths that we would take. We walked the one from the eastern city and this one was a lot nicer. There was more room. It was a little less mountainous. So we figured that that would be the best choice. And when we were in Panama, in addition to walking these paths, we were able to survey them. So we had relatively accurate GPS points, relative elevations, and distances to get from the connection point to our tank locations. We took all this information that we collected and we put it into EPANet to model this system, which is what is shown here. This is that general look outline of our model. It kind of looks like a constellation, but it makes sense. We were able to put in there the elevation changes between the points and approximate locations for our tanks. Those are a little less accurate since we were not able to actually walk to the tank locations themselves. But as you can see on the screen here, I have elevations listed next to the locations, and from the connection point, which is right at the top of the screen, to the northern tank, there's over 400 feet elevation change, which is a massive elevation change, and we needed to be able to pump water up that to get it into the tank. So after some research and looking into different pump curves and such, we determined that pumps in series was the way to go for this. And so the image on the screen is an approximation of the pump that we used. It's by the same company that I based the pump curve off of. And so with pumps in series, based on this pump curve, we were able to accomplish 400 feet of head with about 125 to 150 gallons per minute as a flow rate, because we want these tanks to be able to be filled in a reasonable amount of time, not take forever. Just to tidy up the supply system, we had to locate some valves just for standard maintenance and operation. So we included shut-off valves, which are shown in red on the map of our model, so that we could cut off certain parts of the systems if there was problems or we needed to clean certain parts of it. We also included clean-out valves because in case there does get sediment in these pipelines, it will settle out at the low points. And for this system, there's a major low point right after the connection point. We included clean-out valve locations there in case sediment, we can flush it out. And we also included check valves in this system along the pathway up that really, really steep hill in order to prevent backflow, because that can damage the pump and we want this to last as long as it can. All right, now I'm going to get into the short-term alternative system. So in early December, our team received word that the connection point we wanted to use in Villa Gracia, which is currently under construction, had experienced delays. So we would not be able to use it as a connection point for several years. And the goal is to get them water as soon as possible. So they asked us to come up with an alternative design. And so we did the best that we could. So we chose the connection point in the eastern city of Cerro Pinon. Point 18 is what they called it. So we often refer to this design as the P18 model. So while this point is pressurized because it's attached to a pressurized municipal system, we modeled it in EPANet as gravity fed due to some limitations of the software itself. And we weren't able to do a full in-depth design due to time constraints because we received word of this delay fairly late into the semester. We were able to make a skeleton model as a sort of proof of concept that this connection point could work. It is similar to the other supply system in that it will supply the same tanks that we had earlier. It just has a different connection point and it is more gravity fed as opposed to pump based. Similar to the other one, we had to include valves for standard maintenance and operation, shut-off valves in red again for cleaning or in case something went wrong. Clean out valves again for low points because there was more low points on this path because it was very mountainous up and down and very narrow too. And then in addition to a check valve, which in this case was not to protect a pump, but rather to prevent backflow and potential contamination from going back downstream. We had to add an air release valve because there was a pretty high point at this, along this path, and then if there is air that gets trapped in the system, we need a way for it to escape. We did not choose this originally, the 0.18 as our connection point due to concerns with constructability, because we walked this path and it's extremely mountainous and narrow at times. So we felt it wasn't the best choice. But more so in the long term, it's still not the best option because it will put potentially too much strain on the system in Cerro Pinon because it is a smaller system than Via Gracia. So that's why long term, we still recommend the other supply system. However, in the short term, this might be the way to go to get them water while the construction is finished up in Via Gracia.
So the next portion we're going to talk about is the distribution system. And I've broken this up into going over a brief design overview to cover some of the basics and then going more in depth on the pressure reducing valves and important locations for regulating those pressures, and as well as storage tank alternatives and elevation restrictions. And then we'll go through the results. So a brief overview, this design is modeled as gravity fed because it would be gravity fed from the two storage tanks we talked about. And it is broken into two smaller distribution systems with the north tank supplying sectors 3 and 4, and the south tank supplying sectors 1 and 2. The reason the south tank is almost twice the size of the north tank is because sector 2 holds the majority of the community's population. And so we mentioned this in our assumptions because if our predictions on population distribution, which are based off what we could see from Google Earth, are incorrect, the tanks may need to be resized if they're significantly incorrect. In the EPA net model, each of the nodes represents between 1 and 12 houses, each of the demand nodes. So this is not referring to our surveying data along the roads. This is referring to the houses. We put them in clusters, and the clusters are based on shared elevations and proximity. So we were looking on Google Earth at how many houses were close to each other and what the elevation change between them is. Sometimes houses were very close to each other, but they had 50 to 100 feet elevation changes between them. So they were modeled as separate nodes. The system is designed to be made out of Schedule 20 PVC, 2 inches for the water mains and 0.5 inches for service lines. We've also included in this design locations for shut-off, air release valves, and clean-out valves. Air release valves are located at relative maximums and are shown in blue, and the clean-out valves are located at relative minimums and are shown in yellow. So one of the most difficult problems to solve with this design was regulating the pressures to get between that 15 and 75 PSI goal. 15 is the ideal lowest PSI, but we set our absolute minimum at 7 and considered that the absolute minimum for adequate pressures. And above 75 PSI poses problems for plumbing fixtures such as toilets. So we have to keep at least houses below that limit. To do this, we have used 4 pressure reducing valves and have located the highest downstream points for them in order to determine what they could be set at. So for the first pressure reducing valve, this is determined by sector 3 cluster 3 shown on the map, which have an elevation of 902 feet and is significantly higher than any other houses around it. So it determined what our minimum pressure setting according to the size of the station. For each of the other pressure reducing valves, we've also determined a downstream high point. The only exception to this is the third pressure reducing valve, which occurs right before a 210-foot drop. So its setting is kind of irrelevant. You could set it to 0 and it would still go pressures back up to reach sector 122. Oh yeah, so those are the pressure reducing valves that are on water mains, and then in the results section we will talk about some remaining high points. So another thing that we wanted to verify and define was the minimum elevations in reference to another point in the community of our tanks. We know that there are some errors in our elevation data due to the surveying equipment used and due to pulling things from Google Earth. We tried our best to make things make sense and based on the information we have, but we know that our elevation data is probably not entirely accurate. So we wanted to determine in reference to another point in the community what the minimum elevation would be. So for the north tank, this is sector 4, cluster 22. This is the highest point in the community, is one house, and it is 995 feet. We determined that in order to supply that point, the tank needed to be at least 15 feet higher than it. And if it can supply this high point, it would be able to function with all the pressure reducing valves and all other high points in the community. In that half of the system. For the south tank, we determined that the local church, which is sector 2, cluster 29 in our model, and has an elevation of 950, would be the determining factor. And again, we found through playing around with our model that it would need to be about 15 feet higher than this point to provide adequate pressures. And in this, we are saying absolute minimum pressures of 7 psi, and so you need at least 15 feet elevation difference to get that. Additionally, if the tanks were too high, we believe this problem could be solved with the addition of 2 more pressure reducing valves and water mains. So that wouldn't be too big of a deal. We would just have to cut the pressures more quickly right away. In our report, we do cover a few more specific alternatives if the elevations of the tanks are higher than predicted. But at minimum, 2 more pressure reducing valves would be able to solve any high elevations. So the results of this design is the figure, right? And the yellow dots represent pressures between 13 and 75 psi. So as for low pressures, we have 3 locations that do drop below the 15 psi at certain points in times of the day, but none of those drop below 10 psi. So they're still considered adequate, and we do not think that it is a problem given that they will still have adequate pressures and they're not much below the 15 psi. As for high pressures, there are a significant number of orange clusters on this figure, and those are pressures above 75 psi. So these are points that we couldn't reduce with a 2-inch pressure reducing valve on the water main due to up or downstream high points. But we've counted them out, and we believe that 17 0.5-inch pressure reducing valves would be able to reduce those pressures down below 75. And those would be put on the service lines or the service mains for a number of different houses. And then there's very little daily fluctuation. We can't show in the figure all the times of day that we modeled, but on average, most clusters had less than 2 psi in changes throughout the day.
So with all the design stuff figured out, we had to come up with some important estimates. The first of which would be a rough construction schedule. As mentioned, there were 2 other groups that took on the project before us, and they gave estimates of 80 and 180 days respectively. Now, to be fair, they weren't there on site, but those estimates just aren't realistic. We kind of gave it a look over and took the important tasks that need to be done at hand. And with that in mind, we kind of gave a rough estimate of 196 days. Now, this assumes that a lot of things are going right. It assumes that they have the equipment, the tools, and the labor that they need, and that there aren't any delays due to things like inclement weather. So with all those things in mind, we gave kind of a rough ballpark of 196 days to complete this project. Second important estimate is the cost of this project and the bill of materials. The important thing for our partners in Panama was that we provided them with a bill of materials more so than a construction cost estimate, because in Panama, things like different parts might have different costs, or they simply might not be available in the same types or brands that are on hand here in America. So we provided them a bill of materials, which is long and boring, and you wouldn't want to look at it here. So for better understanding, we provided a rough cost estimate. So keeping in mind these current market conditions in America, if you were to build such a similar project here in America, we kind of gave a rough ballpark of $250,000. Now, as with a piece of IKEA furniture, we're going to want to account for any missing pieces. There could be things that we overlooked or parts that just weren't accounted for. And for that, we increased the overall cost by about 15% for a total of $290,000, just in case there's anything we overlooked.
So we wanted to go through some of the recommendations we have and next steps, as well as some general discussion points that we address in our report. For this design to move forward, one of the important things that needs to be done first, considering that we completed this design remotely other than our week in Panama, is the verification of those minimum tank elevations, as well as verifying if the land that we have selected would be possible to build on, and if not, to make adjustments for qualifying that would be possible to build on. Additionally, because we received such late notice about the difference in days, our P18, our serial P1 short-term model needs to be evaluated and verified and completed if necessary. We did our best with the time we had, but we had very little time to work on this system, and so there may be some things we overlooked that need to be completed. Additionally, we would like to acknowledge some of the potential impacts of this system. As Melina mentioned earlier, this is built on the same watershed as the Panama Canal. And with the effects of climate change moving forward, the Panamanian government is concerned about freshwater demands in this area. So this is a more long-term problem that needs a bigger solution than what we can provide. And we also wanted to address that with increased water usage, there will be increased wastewater demands. We were not informed about the current state of their wastewater facilities, though based on our time there, we believe it to be some kind of septic tanks. But with increased water use, these would probably need to be updated or a municipal system installed in order to properly deal with the increased wastewater. We would like to acknowledge our advisor, Dr. David Watkins, as well as our partners at Local Possibilities. They were with us every day while we were in Panama and have since been helping us gather information remotely. And we'd also like to acknowledge the community of Macombo Arriba. They were very kind to us when we were in and helpful, and we really hope we can make this happen.
That concludes the presentation. Now we can open it up to questions from everyone. Yep.
Did you look at a cost benefit for operating that utilities and the cost of building it to maybe just in putting storage tanks there or in the cities and just getting more trucks there? Is there a cost benefit to running that all the time?
It's not, we didn't do a cost benefit analysis on that, but the problem with the tanker trucks and like, because they currently do that, they just have storage tanks. Most everyone has one at their house. And then the trucks come by. The problem is the reliability of the government in that case, how like they don't get the trucks there when they say they're going to. The trucks are supposed to come by, I think, every 2 weeks.
I think it's
Yeah,
everyone.
and
Every 1 week, and sometimes they don't come by for 2 months. So it's more of a like reliability thing that it's not really a cost, it's just like it's not gonna happen.
An additional concern that we were informed of when we were in the community is that the water from the tanker trucks only stays potable in their storage tanks for about 3 days. So if they're going 2 months without getting a new shipment of water, like the tanker trucks would have to be coming every 3 days for that to be a good solution. And so we didn't do a cost benefit analysis, but we do believe, based off what we learned in the community and what we've done research on, that that's not really an option.
So you guys were talking about how sometimes in different places it was hard to get that correct pressure for distributing throughout the rest of the community. Did you guys look at water towers by chance and introducing water towers to try to increase pressure throughout the system? I know that's something that we do commonly here.
We do it commonly here. The problem is the cost of water towers. We had at one point asked our advisor what the general cost would be to raise a tank even 10 feet, and it would be a couple $1,000. And also given the topography of this area, it would be a lot cheaper to just move it 10 feet up the hill. Because this is a very, very mountainous area, and that's a cheaper way to get that elevation needed, which is what we're currently doing. We have these off the roads, these tanks up ridges that we saw while we were in the community, and then also can see on the topography maps.
Yeah, so we've talked a bit about the elevations, but I would say definitely after being there that the roads that we were going up, put the Houghton roads to shame.
Yeah.
They were insane.
It's like Houghton, we have very steep slopes going down toward the portage. In this area, they have up and down, over and over and over again, which is why this community has such strange elevation changes. Yes.
Do they have big seasonal differences in the wet season, dry season that affects your pressure issues, or like, is that something that's gonna be essentially upstream of your problem?
So from what I understand, we are connecting to the municipal system that serves most of Panama City. And we have not been informed of any water shortages caused during the dry season at this time. That might be a problem in the future with climate change, given the strain the Panama Canal puts on this watershed. But we have not been informed of any issues that the connecting the municipal system would pose. Anyone have anything else on that?
We'll say it is one of the last cities in the area to receive water, and this is primarily due to construction feasibility. A lot of the other areas were, are currently under construction, or they just finished construction, and they did the easier areas to construct first. So this is the last one, so this wasn't the hardest one for them to feasibly construct at this point.
You put both towers in and you fed the one from the north, could you then feed back 0.18? For redundancy purposes?
I do not know, and I do not know what the purpose of that would be. We do not have a model for the Seraphim system that's currently undergoing construction. And we don't have any information to look at what's going on that side of 118. We can only really look at what they told us were the pressures and the elevations at that point. The thing we did look at, and that due to limitations of EPA net and our understanding, we didn't end up doing, was interconnecting the two tanks, the north tank and the south tank, so that all of the sectors were interconnected. The reason we didn't do this is because we weren't sure how to properly size the tanks if we didn't know where the water was going. But that would be a way to increase redundancy, is if the tanks were built a little larger than expected, and the connection between sector 2 and sector 4 was reinstated.
One thing that the Panamanian government was also worried about is people illegally tapping into the system. So part of that is we wanted to absolutely minimize any potential chances that people might be doing that. So that's why we originally chose a shorter route with like no chance of people doing that compared to some of the other ones we looked at.
Are earthquakes an issue?
No.
No, not really for Panama, the way that they are located, I think they're in the middle, they're their own.
They're their own tectonic plates.
So they do not get earthquakes.
We got to go to the Natural History Museum.
Yeah.
And while we were down there, and they explained the tectonic history of the area, and there are volcanoes off the coast, but Panama itself does not have the earthquakes of surrounding Central American countries because they are their own little tectonic plate, just kind of like floating in the middle. And so they don't have much of earthquakes.
They said it's gonna take 7 days to build the concrete foundation. Is it for both plants or?
It's assuming that they're being done in conjunction of one another at the same time. Yeah. It's
What's underground, what are they building the foundation on?
they're just building it on as flat of an area as they can find in relation to the topographic points.
What is the underground material like? Is it rock, soil?
No, we didn't get to do a soil analysis. We did include some material costs for gravel for putting it underneath for drainage purposes. But other than that, we don't have a great idea what the soil is around there. But we were assured that they do have good experience with building these kind of tanks.
Our partners are Open Possibilities NGO partners. Have said they built these kinds of tanks in similar areas. We did include in our discussion, in our report, the potential possibility of earthwork being needed. But that is outside of our knowledge of these areas. We don't have good enough photos of the areas we're proposing to know if earthwork will be needed.
From walking around here, no. No, but you saw a lot of clay, right?
Yes.
A lot of clay and even a lot of bedrock.
Yes.
Exposed bedrock even. Which is part of originally why we didn't choose the connection point in the east is because of that.
It would have to dig through in some places bedrock or be buried in cement above the bedrock.
What, do you know what the bedrock is?
It was gray.
Yeah.
So you're doing all this planning, I believe, if I understand correctly, on a population of about 2,000 people in this
Yes.
area. So I was just wondering if you had any sense of how the population may have grown recently and therefore how much it may grow in the future?
So, when we were in country, we had a brief meeting with officials from Adon, and they are very concerned about population growth in the area. So they specifically told us not to include population growth in our design, and instead of including population growth, we have done a 10% contingency on our tank storage and most of our values, just to make sure that if our population estimate is not accurate, we are supplying the current population and small amounts of growth. But our hands are a little bit tied because they're the ones who will approve or disapprove of this project.
Ultimately pay for it.
Yes,
So
so,
I imagine being a kind of a remote area, it's hard to get sort of census data. like that.
yeah, the census data we were given didn't include kids.
Right.
So,
See if there are any questions on Zoom.
Will we be able to hear them?
Nobody's talking. It was nice.
We can ask if they want to type a question into chat.
Yeah. Questions in the chat. Let's see if you have any.
I don't know what one's that.
That open chat.
any other questions?
How many days were you in Panama?
A week, 7 or 8 days technically, I think, but the last day was like flying out, and we had one day to do like more of the touristy things, where we got to go see the canal, so we were in the community for like 6 days, yeah, 6 or 5 days, so very short amount of time. Yes.
Yeah. They had really good food. The local community fed us lunch every day, so we were getting real good food.
Yeah.
Plantains are really good when they're not like brown and mushy at Walmart.
Get to see the new part of the canal or the old part.
We probably did part actually, yeah, the extension.
I don't think so. We saw the old part, but we could see
We
up
could
the
see
hill,
very far away,
the
the
new
new
part.
parts. We were in New York.
But I think the these or the tourist stuff for that is on the other side of Panama.
Yeah.
Not the Atlantic side, which we were not on.
Great, thank you. Thanks everyone for attending the long haul presentation this morning. Appreciate your sticking with us.
I was on and this was.
Oh, yeah, they did.
There was like a 30-minute break time between us and the previous group, so there was no group right before us.
Very high progress.
Oh, you guys are safe in your.